We're going to go over operations with vectors, this time three-dimensional space. So a little more complex than we had been doing it before. In 3 space, or at least in 2 space, we talked about unit vectors. We had talked about I being the unit vector, so a value of 1 along the x-axis. J being a unit vector, value of 1 along the y-axis. And because we have a third dimension, they now use the unit vector denoted as vector k with a value of 1 on the z-axis. Okay? So all of these are unit vectors, and usually when using I, j, and k, what they're doing is describing maybe a positional vector in 3 space, or a vector sitting anywhere in 3 space, and we're using scalar multiples of these unit vectors to create these larger vectors. Okay? That's the idea of a unit vector. Just like we did in 2 space, we use scalar multiples to find those points. Our positional vector is still very similar to the same idea that our coordinate of A, B, and C, so our x, our y, and our z, are essentially the scalar multiples we're going to use on those unit vectors to create that positional vector. And like an extension of Pythagoras Theorem with just one more dimension, the formula holds true that if we're trying to find the magnitude, or think of it like the hypothesis of those 3 unit vectors together, the magnitude is essentially Pythagoras Theorem with one extra dimension to it. Okay? So let's talk about this part to start, not that part, the top 2. So we'll go down here and zoom in a bit. Don't blow up on my computer. There you go. Okay, so we go down. We have 3 space here. And let's talk about just a positional vector. Call it point P, which can be at, oh, and let's talk about, this is our x, this is our y-axis, and this is our z. Going up with z is positive, okay? Going to the right with y is positive, and coming forward with x is positive, okay? And vice versa for negatives on this 3-dimensional graph. Our points here, let's call them 4, -6, and 2. Okay? So the very first thing we got to do is actually find where this position is in space, or in 3 space, let's say. And we know we can turn this into unit vectors, or represent this as unit vectors, by putting these in front of the denoted unit vectors for 3 space. So I could also represent that point P, or OP, our vector OP, as being, this being our scale for our x, and remember x is represented by vector I, so our scale is 4 minus 6 vector j plus the scalar of 2 for vector k. Okay? So the idea here is, let's try to make very small unit vectors for each. I think we did x as red. The unit vector for I would be 1, so 1 would be about half of this. Okay? Because there are 4 altogether, we have to actually go all the way to the number 4. So we use that unit vector to the scale of 4 to get to this point. We'll use green for j. J being our y-axis being -6. Our unit vector is a scale of 1, so that's roughly what the unit vector looks like. We have to use it at a scale of -6. Sorry, and apologize, because normally it's +1. And because our scale is -6, we go in the opposite direction 6 units, okay, from the origin. Okay? Remember, we're moving directly from the origin here. And finally, the last one we deal with is k. We'll do that blue. Sorry, yeah, k. And k deals with z, z being a value of 1, so here's our unit vector. And because it's 2 in this case, we only have to go up 2. So what we'll do is we'll create, we're going to create our parallelogram using these ideas here. Let's do green. Green has to come across 6, which is 3 of those. 1, 2, 3. Okay, go back to blue to get the other z. Go up 1. And then our x came over here. Okay. So we're using our parallelogram. These are all of our x values in red. Our blue values are the z's, and our green values are our y's for the parallelogram. The idea being our coordinate of P, and we're going to denote it very obviously, is going to be there. Okay? And that is going to be the point that is at 4, -6, and 2. This is our point here. So to draw our positional vector, put it in black, we go from the origin to this point in space. Okay? And what we did is we used 3 different types of unit vectors to get there. Okay? So we used those 3 unit vectors to create this positional vector. Hopefully it made sense with this parallelogram here, that this is where that point is P in space. Okay, so this is our point P in space. So we've now drawn our positional vector here. If we wanted to find the magnitude of this positional vector, okay, we're going to be using Pythagoras Theorem. So I'll try to use dotted lines here at this point, though they might be a little hard to see now. The idea being that we've used 3 kind of triangles to get to this point. There is the triangle along the x-axis, or sorry, I should say the xy plane. We have this triangle here. This is using our xy plane. We also have a triangle we've created from here. It's really hard to see. I don't know if that was very helpful, okay? But we have a, well, it looks like a vertical triangle, and we have a kind of flat triangle here, and we're using Pythagoras Theorem quite a few times to actually find the magnitude of that black line. It's much easier to see if we actually write it as a formula. Okay, so the magnitude of OP is our values of our unit vectors. Okay, so this unit vector here, formula being a squared, b squared plus c squared, and this is also squared here. Okay. So our a value, which was 4 in this case, we're left with 4 squared plus -6 squared plus 2 squared. That was our c, or k, our scalar in front of our k. It's going to deal with the magnitude of OP. So we need to find, oh sorry, I already drew the root. I don't square this, my fault. So we need to find the square root of these values, which is 16, 36, and 4, 40, 54, root 54. I believe that'll be root 54. So the magnitude of our positional vector in space should be root 54, whatever that is on our calculator. Okay. So that's kind of taking care of these first 2 rules here. That's the idea of this. We've drawn a positional vector in 3 space, and we found the magnitude using the unit vector. Sorry? Oh, is it 56? 36. And 4 is 40, and 16, yeah, you're right, it is a 6. 56, thank you. Okay. Okay, so I spared you, and didn't, well, in class I made you watch me, but on the video you didn't have to watch this part. I've drawn in 3 space our vector, technically positional vector OA, so it's starting at the origin going to A, and positional vector OB. And the reason I've done this is because I want to highlight in 3 space, which is going to be very hard to see, but I want to show you guys the idea of vector AB in 3 space. Essentially, AB will be from this point in 3 space A to this point in 3 space B. So we said we're going to use green. So that vector is going to go from A to B. Okay? So this vector is going all through 3 space, and I want you to really see the depth of this. This A is in front of the x-axis, while this B is, the y-axis, is behind it. So this is essentially going above and crossing over, okay, in 3 space. That's what that vector is doing there. So it's doing quite a bit. Very hard to get an idea when drawing on a piece of paper what the magnitude of such a vector would be. Okay? So first of all, we want to turn this into a positional vector. Well, we have the coordinates. Okay, so because we have the coordinates, technically the idea of this positional vector, which we're going to find, is I'm just going to clone it, and this is actually going to go off the chart, but its tail here should be at that origin. Okay, now obviously this one went so far up it went off the chart, so we're going to actually use some math to figure out where it ended up, where the tip of this one ended up. So we're going to take our A point here, we'll call this our coordinate 1 and our coordinate 2. Okay. So we take our coordinates here, And we are going to use in 3 space our x2 minus x1. Another coordinate will be y2 minus y1. And our last coordinate will be z2 minus z1. Okay. So this will be my x1, y1, z1, x2, y2, z2. Okay. So our x2 in this case is -3, subtract 2, 6 subtract 3, and 4 subtract -1. Okay. So to find out where this OP, or vector OP would be if it was a positional vector, we're going to get -5, 3, and +5. Is that right? -5, 3, and +5. 3 and +5. Yeah, so it does go off the chart. That makes sense. So as a positional vector, it's exactly where we had pointed it. It'd be deep and kind of off this chart here. Now, what this is important for, if we were to draw this as unit vectors, right? Remember, these x's are represented by unit vector I, our y values represented by unit vector j, and our z's are represented by unit vector k. So as a combination, okay, of unit vectors, we have -5i plus 3 vector j plus 5 vector k. This information is very important because it will help us, instead of using the large formula, whereas the distance formula, kind of like Pythagoras Theorem, we can just go back to the other theorem we had before if we want to find the magnitude of our new positional vector OP. We're going to find the root of this being A, B, and C, these scalars. Okay, so these scalars will help us find the magnitude of it. We're going to take our A squared, just like we did before, B squared, and C squared. Okay. So our A squared is going to be 25, B squared will be 9, and C squared will be 25 again. Oh, there we go. We should be getting root 59 as the magnitude of our AB vector. Okay? So this is kind of the 2 pages together. So all I did here, and I know they've given you a different formula, but at this point here, this formula, I just did the distance part separately and made it a components of unit vectors. So we use standard unit vectors to describe this, and then we use the scalars of those unit vectors to put into our original one. But the idea, this formula is essentially this formula here. They just made us do one more step, and I decided to do it separately. You can do it all in one if you like, or you can break it down into different steps and try to make sense of each step as we go through it.